The Louis Burke Frumkes Center for Writing and Culture at Hunter College presents 10 years of best-selling authors and great thinkers.
I'm going to begin by introducing Charlie and telling you a bit about tonight. And afterwards, Charlie's going to talk for about 40 minutes, and then afterwards, you may ask him questions for a short time. Not too long, because he has places to go and equations to conquer. So, good evening. 2015 marks the 100th anniversary of Einstein's invention of the general theory of relativity, one of the two pillars of modern physics. The other is quantum mechanics. Together, these two formidable theories underpin our current understanding of what we call the universe, or cosmos. In fact, the theory of relativity may well be the most famous theory in the world. Certainly, E equals mc squared is the most famous equation in the world. Yet while everyone has heard of the theory of relativity and acknowledges its importance, few outside the rarefied area of mathematical physics actually understand it. This is because it is an enormously complex mathematical theory and beyond the ken of most of us, even most science professionals. Thus, I have asked an enormously intelligent and gifted mathematician from Princeton, who teaches where Einstein once taught and who understands the mathematics behind the general theory of relativity, to come to Hunter College as one of the Writing Center's great thinkers and to explain the theory of relativity to us and the mathematics behind it in terms we actually may be able to understand. No mean feat, to be sure. So just who is Charlie Pfefferman, this gentleman, and what makes me feel he is up to this formidable task? Well, for one thing, he is a Fields Medalist in mathematics, the mathematical equivalent of the Nobel Prize, which Einstein won in 1921 for his services to theoretical physics. Charlie won it for his work on partial differential equations, Fourier analysis, in particular convergence, multipliers, divergence, singular integrals, and Hardy spaces. As you can imagine, there are only a handful of Fields medalists in the world. Charlie also won the Alan T. Waterman Award in 1976, the first person to ever get the award, the Salem Prize, the Bochet Memorial Prize, and the Bergman Prize, not to mention election to the American Academy of Arts and Sciences. Suffice that Charlie's awards and honors fill several pages, which I don't have time to cite here. Despite the fact that this may embarrass him, I should tell you that Charlie Pfefferman was quite precocious in his development, having entered college at the age of 11, receiving his PhD at 20 from Princeton, and achieving a full professorship in mathematics at the University of Chicago at the tender age of 22, making him the youngest full professor ever appointed in the United States. From what I can tell in dealing with him, Charlie is also as nice as he is bright. Thus, it gives me great pleasure, ladies and gentlemen, to present Charlie Pfefferman to you as one of the great thinkers in our series who will explain Einstein's general theory of relativity to you. Charlie?
Thanks. Well, so Louis, thanks for the very flattering introduction. I hope I get to introduce you sometime. Let's see. All right. The general relativity is a collection of wonderful ideas which are seldom explained to the general public, and when they are explained, the explanation consists of taking out the math. This makes a mathematician cringe. I think it is possible to explain the math without writing a lot of awful equations and in 40 minutes. Let's see, okay? So the math behind general relativity is a certain kind of geometry. And so I'd like to spend most of the time talking about geometry and then a little bit of time talking about special relativity. We won't mention such minor details as E equals mc squared, but you'll see anyway, did I say general? Special relativity, the main point of special relativity if you had to explain what special relativity is in 2 minutes, what would you say? Well, you'll hear what I'll say. Okay? And then I would like to give the introduction to general relativity, where all of the ideas come together. Okay, so let's start with geometry. Okay, now, all right, so there's an illustration. That's my first slide. My second slide. I'm off to a flying start. Let's see. So the Greeks, Euclid in particular, had the wonderful idea that geometrical knowledge could be deduced from a few self-evident axioms and postulates. These were so obviously true that one could not doubt them. And yet, by logic from them, you could deduce all kinds of amazing things. That was a fantastic idea. The Chinese and the Babylonians knew a lot of geometry, but I think it was only the Greeks who came up with the idea of proof from axioms. But one of the axioms struck the Greeks as less obvious than the others, and it's the parallel postulate, which I've illustrated. Let me explain. I remind you, or explain as the case may be. The parallel postulate is one of the basic assumptions of Euclid's geometry, and it says the following. Suppose we have a here. Where'd it go? Oh well, forget it. We have there we have a straight line, and here's a point not on the straight line. Passing through that point, there is one and only one line parallel to this one. Remember, parallel means that the lines never meet. Okay? Now, let me speculate on why the Greeks decided that axiom was less obvious than the other ones. Okay? And my speculation is that if you think about the known world, here's the Greek world with the ocean river surrounding it, okay? You can't tell in the picture, given this line, you can't tell whether either or both of those lines will ever meet it, because you can only go as far as the edge of the known world. So it's not obvious that there's one and only one parallel line. That's only a speculation. I wasn't there, okay. But that was regarded as less obvious than the others. So everybody believed it, but still the question was, could this statement be proven as a consequence of the other axioms and postulates of geometry, which were regarded as even more obvious than this one? Okay? And people tried to do that for a bit over 2,000 years with no success. It turns out that it is impossible to prove the parallel postulate from the other postulates, and there's a reason. And there's also a reason why nobody thought of it for 2,000 years, which is that it required a very profound change in the point of view. Until the beginning of the 19th century, the way people thought about the axioms of geometry was that they were obviously true. They are God's truth. You may not question them.
Forgive me for interrupting God's truth for 1 second. When you walked over here before,
yes,
your mic didn't play for the people in the back. If you want, this is a handheld one.
Will do.
Might work better.
Okay, great.
Okay.
Testing, 1, 2, 3, testing. Can everybody?
The pointer worked when you used it. Okay,
And the pointer worked also. All right. Pointers are my enemies. I'm going to. Okay. But can everybody hear me?
Yeah.
Okay. All right. I'm sorry about the glitch. In any event, let's see. Okay. So the axioms and postulates of geometry were true, period. Okay. The change in the point of view was, well, you know what? Maybe they're not true, and we should think about whether they're true. In fact, we should go out and measure whether they're true. Geometry is a collection of statements about lines and angles and circles and triangles, and, well, let's go out and look at some actual lines and circles and triangles and whatnot, and let's see whether geometry is right. One key event in this intellectual development, I'm oversimplifying the history. For that matter, I'm not an expert in the history of math, but one crucial event was the request or the order by the Duke of Brunswick to a great mathematician of the 19th century, Gauss, to undertake a survey of Brunswick. So I must say I've never been to Brunswick. I haven't looked up what it looks like, but I'm making up here an imaginary topography of Brunswick. Now suppose that the two red dots in the picture are towns in Brunswick, and you want to walk from one to the other. You want to take the shortest route. Aha, the shortest distance between 2 points is a straight line. But if you live in Brunswick, that's not a very useful statement, because you can neither fly nor burrow under the earth. So you stay on the surface of Brunswick, and you take the shortest route you can, which is called a geodesic. Okay, so there's a picture of a geodesic in the imaginary topography of Brunswick. Now, it occurred to Gauss, let's think from the point of view of, let's say, an ant living in Brunswick. The ant is, let's say, not at all aware of the three-dimensional space in which Brunswick lives, but is only aware of the surface of Brunswick. What kind of geometry would the ant develop? Well, the ant, let's say 2 ants would stretch a string, and they would find the geodesic, and that's what they would call a straight line, just as, let's say, you and I might pull on a string, and the shape of that string would be a straight line. Okay? They would measure angles between geodesics, just the way we measure angles between straight lines. Okay? And they could, for example, draw a triangle made out of geodesics, and they could check whether, for example, the sum of the angles of a triangle is 180 degrees, the way Euclid teaches. And they would find that, all right, what would they find? Let's say the surface of Brunswick is very smooth. It doesn't contain any sharp corners. Well, if the ants stay in a small part of Brunswick, they are not going to notice that Brunswick is curved, and they're going to think that Brunswick is a plane, and perhaps they can read their little miniature copies of Euclid and decide that that's the way geometry is, and the sum of the angles of a triangle should be 180 degrees, and if their triangle is sufficiently small, the sum of the angles of a triangle will be close to 180 degrees. But then the boulder of the explorer ants will go out a great distance, a few kilometers perhaps, and there will be bigger triangles, and the sum of those angles will not at all be 180 degrees, and Euclid is wrong. It's only approximately right if you look at something small. And the fact that it's only approximately right reflects the fact that the world is curved. Okay? Well, stupid ants, what do they know? Well, let's see. Let me actually delay that for a minute. Well, we humans lived on a sphere for a long time without realizing that it was a sphere, and we thought it was a plane, and Euclidean geometry seemed right, but on a sphere, Euclidean geometry is wrong. And what's wrong? If you go through either on Brunswick or on the surface of the Earth, where, let's say, the shortest distance between two points is a great circle, that is a circle obtained by cutting the sphere with a plane passing through the center. Okay? For example, the equator is a great circle. So that's an example of what we on the Earth could call a straight line. If you go through Euclid's axioms and postulates, you find that they're all correct except the parallel postulate. On the sphere, there are no parallel lines because every 2 great circles meet. Okay? So here's an example of a geometry in which all of the assumptions of Euclid are correct except the parallel postulate, and the parallel postulate is wrong. So the parallel postulate could not possibly be a logical consequence of the other axioms of geometry, but in order to see that, you have to think in relative terms about what the axioms are telling you. Okay, now still, if you look either at Brunswick or at people on the sphere, we could still be left with the condescending notion that they just don't get it. They see only a part of the world, and we see the whole thing. We see the whole three-dimensional world, and all right, their geometry is not like ours, but it's because they don't know better. The next few examples are intended to shake your confidence that that's true, that in fact other geometries are just as likely to be true as ours, for us. Okay? So the next picture is an illustration of the Poincare half-plane. So imagine we are in space, well, let's say two-dimensional space. And here are people, but for some reason, because I don't know, God knows why, as we approach the floor, see the floor in that picture. As we approach the floor, we shrink. Let's say that our size is proportional to our distance from the floor. So the creatures in this picture are very strange, shrinking creatures. Notice in one corner a creature very, very close to the floor and therefore very, very small. Now the creatures don't notice that they are shrinking because they bring with them a ruler and they use the ruler to measure themselves, and the ruler is also shrinking. Okay? From their point of view, if they could see us, we would be extremely strange creatures that grow depending on where we are. Okay? It looks rather strange to us that there is an edge of the world, but if this little creature walks toward the edge of the world, he shrinks as he approaches the boundary, and he never quite gets there. Okay? If you're familiar with Zeno's paradox, this is a case in which Zeno's paradox works perfectly, and the bold explorer heading toward the edge of the world will never get there. Okay. Here's a geodesic in the Poincare half-plane. Poincare is the great mathematician who invented this among many, many other things. Imagine that two people located at the red dots want to pay a visit. Let's say one of them stays fixed and the other one wants to visit. It's a mistake to take a straight line because the red dot paying the visit is very tiny because he's close to the boundary. It pays for the visitor to spend some time and effort moving away from the edge of the world in order to grow, in order to make it easier to visit the other red dot. Okay? And so it turns out that a geodesic in the Poincare upper half-plane is a circle, a particular kind of circle. My artistic abilities being what they are, this is my attempt to draw a circle. Okay, and here we have three circles that make a geodesic triangle, and notice that the sum of the angles of a triangle sure isn't 180 degrees, it's much less. That reflects the fact that the Poincare half-plane is curved. Euclid's geometries are approximately correct for a tiny triangle, but very, very far off for a big triangle. Okay. In fact, in this world, the Poincare world, a small circle of radius r has area approximately pi r squared, as in Euclid's geometry, but a big circle of radius r has area tremendously bigger than pi r squared. I've just been to a lecture where somebody actually put the numbers on a slide. I don't have time to do that, but enormously, many millions of times larger, much incomparably larger as r gets big. Now, okay, is our world like this? Well, our world is three-dimensional, not two-dimensional, but there's a three-dimensional version of the Poincare upper half-plane. Here's the floor, and imagine that creatures shrink as they reach the floor and grow as they leave the floor. Okay. Is that the way our world is? It seems not, but of course, we shouldn't think about our world, we should think about our universe. And compared to the universe, we are very small. And if we take trips very small compared to the universe, we're not going to notice this kind of stuff. But for example, if we take an enormous radius and we count the number of stars inside an enormous radius, we could ask, does it seem to be proportional to the formula in Euclidean geometry for the volume of a sphere, or does it instead grow much faster? And people have actually counted stars, and guess what? It grows much faster. So the data, the astronomical data appear to fit this weird Poincare world better than Euclid's world. Okay, now here are some still stranger things. This is something called the Flat Taurus. Imagine the whole world is that square, okay? And here's a creature living in that world. But as the creature moves in this direction and sort of disappears off the edge of the world, he reappears on this edge of the world. The creature doesn't notice that anything strange is happening because from his point of view, this point is right close to that one. This point is the same as that point. They're glued together, okay? And so the creature can do that. Or similarly in the similarly in the vertical direction, the creature can travel due south and reappear up north, and the creature himself doesn't notice that anything unusual is going on. Or for instance, here's the most radical thing from our point of view, a trip toward the corner of the world, and the creature reappears, it disappears off one corner of the world, but reappears in the other corners of the world. And again, because certain points are considered exactly the same as other points, the creatures in this world notice nothing unusual. Okay? So notice this is called a flat torus. A small neighborhood in a flat torus looks exactly as Euclid tells us. This time there's no small change due to curvature. If you look at a small neighborhood in a flat torus, well, let's go back. The flat torus, look at a small neighborhood of the middle. It's a little bit of the plane. You can't tell any difference. It's all about what's going on far away. Okay, so now, so a small neighborhood in a flat torus looks exactly as it should according to Euclid. But if you look at the universe as a whole, it's completely different from Euclid's universe. In particular, the area of the whole universe is finite. Okay? Or in 3 dimensions, and there's a 3-dimensional version of this story, the volume of the whole universe is finite. Also, if I leave this microphone here and I travel, let's say, straight up, and I keep going for 50 billion years, in this model of the universe, I will come back to the microphone, and I'll be able to pick it up, and I will have exceeded the 40-minute time limit. Okay? So, so the universe as a whole looks completely different from Euclid's, even though locally that's true. I just want to give you one more, even weirder example. This is called the Klein bottle, after a 19th century mathematician, Felix Klein. So the Klein bottle is again a square with suitable gluings. And so, for instance, as our creature moves down, the said creature reappears from the top, as in the picture. But when the creature moves off the world to the left, he reappears upside down on the, on our right. He reappears upside down on the left. So before reappearing, you reflect in an imaginary mirror there. Okay? And again, if you think carefully, you will see that there is locally nothing wrong with this picture. The little creature does not realize that anything strange is going on. And a small neighborhood of any one point in this world looks exactly like a small neighborhood in Euclid's plane. However, let's look at a strange thing. So that's a sort of American flag. So notice the creature is carrying a sort of American flag in what he would say is his left hand. Do I have that correct? Yeah. Left hand. Now watch what happens. The creature takes a trip, disappears off the end of the world, comes back upside down, okay, and continues traveling, and looks upside down to us. Well, let's say there's no gravity, so the creature isn't particularly concerned about that, but nevertheless is not in the same position as before, and therefore turns around. And so there he's turned around. Notice that the flag is now in his right hand, okay? So this is a world in which any small neighborhood looks exactly as Euclid would expect, no possibility of making any measurements to decide that Euclid is anything but God's truth. But a trip around the world could interchange your left hand with your right hand. And is our universe like that? We don't know. You shouldn't be too confident that cannot happen. And if we take a trip around the whole universe, then who knows what will happen. Okay. So geometry can be very, very strange. Now, all of these geometries are a special case of something called Riemannian geometry. Riemann was a very great mathematician of the past. He was maybe to mathematics what Beethoven was to music or something like that. So I would just like to explain the ideas behind Riemannian geometry. Now let's see, I'm very rapidly running out of time. This should prove interesting. Okay, so what do all these examples have in common? Okay, so how can we make a mathematical theory that includes all of those examples? Euclid's plane, Brunswick, the surface of the Earth, the flat torus, the Klein bottle, and the Poincare upper half plane. Or their higher dimensional variants, 3-dimensional, 4-dimensional, whatever. And all of those are examples of Riemannian geometry. So I would like to explain what Riemannian geometry is, sort of. Okay. So first of all, we have the world. I drew it as a blob. The world is, all right, the technical term for this world is a Riemannian manifold. Okay, a Riemannian manifold. Now this world has on it points. And, well, we're doing geometry, so we'd better have points. And the red dots in the picture are the points. And there are also patches. And the way you should think of a patch is that maybe this world is very, very big. and the patch is maybe what somebody could get to in a lifetime, or what an ant could get to in an hour, or something like that. Okay, so there are patches all over the world. The whole world is covered by patches. Okay, now each patch is equipped with a way to measure distances and angles, because we're doing geometry. But I don't tell you what that method is. Okay, but I do guarantee for you that if we take a patch to be very, very, very small, then we will not be able to tell the difference between our geometry and Euclid's geometry. The sum of the angles of a triangle will be almost 180 degrees with a very tiny error. The area of a circle will be pi r squared with a very tiny error. And the area becomes more, the error, the percentage errors, let's say, become more and more tiny as we confine ourselves to a smaller and smaller patch. Okay? Now, the patches will overlap. And so if there is some curve lying in two overlapping patches, we can work in either patch to compute its length, but we had better get the same answer, because we're talking about the geometry of the world rather than merely the geometry as it looks to a particular observer. And so here's a picture. Here's the world, a Riemannian manifold. It has a blue patch and a green patch, and there's a red curve lying inside the overlap. And so the master of the blue patch knows how to measure the red curve because it lies in the blue patch, and the lady of the green patch can measure the red curve because it lies in the green patch, and they should agree. Okay? So that's a Riemannian manifold. Now, in a Riemannian manifold, there are geodesics. A geodesic is simply a curve for which, if you take any two nearby red dots, as in the picture, then the bit of the blue line lying between the red dots has the smallest possible distance. So it's the shortest possible path between one dot and another. Of course, if you continue, who knows what will happen? Think about a great circle on the globe. Think about the equator. It's a geodesic, but it closes back on itself. And so there are no claims about what this curve does when you extend it very far. That's a geodesic. Okay, all right, now I'm going to skip a whole lot of stuff because I'm supposed to finish by 20 of. La-di-da, la-di-da-di-da, okay. So, okay. Here maybe is the summary. Well, no. Okay, nope. Let's skip that. We've just said on the level that I can cover in the time allotted. We've said what a Riemannian manifold is. Okay, okay, and just notice that geodesics, straight lines, don't always behave exactly as Euclid told us, and that's curvature. Okay, now comes a very quick tour of special relativity. So I think I now have 5 minutes to do special relativity and 5 minutes to do general relativity. I will try to do it. All right, so here are Alice and Bob. They are two observers. Alice and Bob each have a ruler and a clock. They can measure distances and times. They are moving in space, but they are moving uniformly in space. They are not whipping around on a funhouse ride, but instead they're moving uniformly through space. How can they tell? Let's say they look out at the stars. The stars appear to be fixed in the sky, and so they can tell whether they're moving at uniform speed or not. And if they are moving at uniform speed, we like that and we give it a fancy name. It's an inertial frame. Okay? So Alice and Bob live in their inertial frames, but they're moving with respect to each other. Alice would say, here I am at the center of the world and Bob is moving. And Bob would say, I'm at the center of the world, but Alice is moving. Okay? Now, Alice and Bob disagree about distances and times. Okay? But they agree about the speed of light. I would love to be able to tell you why that's true, but that would be another 40 minutes. Okay? So if I had to summarize special relativity, that's the summary. Alice and Bob disagree about distances and times, but they do agree on the speed of light. Okay, now I'd like to show you a little bit about light. So let's imagine that we illuminate a match at the dot in the middle of this picture. What happens? After 1 second, a circle of radius one unit, one light second, whatever, is illuminated, and those are the dots of the innermost circle, okay? Those people sitting there will see the match after 1 second. Twice as far away, people will see the match after 2 seconds. That's a bigger circle. 3 seconds away, there's yet a bigger circle of radius 3 times the original, and that's where they see the match, okay? Well, but this is only a 2-dimensional picture. We want to keep track of distances and times, and so in the next picture we have space-time. So imagine that the world is 2-dimensional so that we can picture space-time as 3-dimensional. Here's space. There's the match. In that direction is time. This 2-dimensional plane represents all locations at time 0. This 2-dimensional plane represents all possible locations at time 1. This 2-dimensional plane represents all possible locations at time 2. This one at time 3. Okay? All right. So now, if we look at all points of space-time, we light a match here at time 0, and at time 1, there is this small circle of locations where you could see the match. At this time, there's a bigger circle corresponding. These 3 circles correspond to the 3 circles in the previous picture, but I've arranged them according to time. Okay, I hope it's clear. Okay, yes, I hope it's clear. Okay, so if you put all of those circles together for all times, you get a cone. It's called the light cone. Okay, and so Alice and Bob don't agree on much, but they agree on the light cone. Okay, and they're, all right, I shouldn't have too many equations, but I have one equation. That's the equation of the light cone. If it makes perfect sense to you because you've taken enough math, that's great. And if it makes no sense to you because you haven't taken enough math, don't worry about it. Okay? That's what Alice and Bob agree on. All right, now comes the intro to general relativity, and I have 5 minutes. All right, so we're going to talk about space-time. Space-time consists of events. That's an event, okay? It occurs at a particular location in space at a particular instant of time. So space-time is the collection of all possible events. An event is a location together with a time. Okay. Okay? Now, space-time, we can't see all of space-time, but we can only see some of it. And so space-time is covered by a lot of patches. And so there's Bob's patch in green and Alice's patch in red. And the dots this time in the space-time represent events. Okay? Now, let's see. Notice that there are some events that Alice and Bob can both observe. For instance, there's a dot in the red patch and the green patch. Those are events that Alice and Bob can both observe and measure. Okay. Now, in each patch, in Alice's patch and in Bob's patch and in every patch that covers space-time, there is a formula analogous to the one I wrote down before that specifies what the light cone is. Okay? So Alice has her light cone, and Bob has his light cone, and we all have our own light cones. We each have a light cone. Now, Alice's formula and Bob's formula agree whenever they discuss what's happening, where and when their patches overlap. Okay? So maybe Alice can see part of the world that Bob just can't see, and there's no question if they're agreeing. But if they can both see what's going on, and Alice asks a question about the speed, is this, look at this particle zipping along, is it traveling at the speed of light? Alice and Bob will agree on that. Okay. Now, all right, I didn't get a chance to introduce even as many formulas as I would have hoped. Maybe that's good. But if you look at this situation with space-time, and if you think about the previous situation with Riemannian geometry, the mathematical theories and the formulas are exactly the same, except that you have to change one plus into a minus. Well, I haven't shown you what the formulas are, so how could that possibly make sense? Let me try to justify it a little bit. If you're measuring distances, you might ask, what are the points of a fixed distance from this center? That's a sphere. If you were doing relativity, I light a match, and I look at all the events that correspond to light passing a given location, light from the match passing the given location at a given time. That's a cone. Okay, so Riemannian geometry somehow has something to do with a sphere, and special relativity, or here even general relativity, has something to do with a cone. And if you think about, either you remember from high school or take my word for it, if you look at the equation for a sphere and the equation for a cone, they are the same equation except that one plus sign is changed into a minus sign. And so you take the mathematics that Riemann did and you change it to, you change one plus sign into a minus sign, and there are some formulas which I'll skip, and you get a version of Riemannian geometry which is called Lorenzian geometry, after the physicist Lorentz, who was one of the immediate precursors of Einstein. All right, so just as in Riemannian geometry, there are geodesics. They satisfy the same equations. All right, I don't have time to, I have one more minute. Okay, so geodesics are the paths taken by moving particles. According to Newton's physics, unless you do something to a particle, it will just travel along a straight line. Well, according to Einstein, what will happen to a moving particle if nothing acts on it is that it will travel on a geodesic. Okay, there is no such thing as a straight line because space-time is not what you think it is, but there is a geodesic. And that's the closest analog of a straight line, and particles travel along straight lines. Now, in the simplest case, let's say this case of special relativity, in which we're not worried about, in which life is simple and the cone is just a cone and the geometry is Euclid's geometry or whatever, geodesics are just straight lines. Particles travel in straight lines. But in more interesting cases, geodesics don't quite behave like straight lines. The motion of particles is not what you might have predicted. Particles move differently from the way you might think. And how is that interpreted? That's what gravity is. Gravity is something that makes particles fall. I throw this at you, or I don't know, I go over in my lecture and you throw fruit at me. It does not go in a straight line because of gravity. Gravity is making things travel in other than simple straight lines. Well, Einstein's explanation for gravity is that it is simply the curvature of space-time. Okay, so geodesics in Riemannian manifolds don't behave as in the simplest case, which would be Euclid's geometry, and that's curvature, whereas geodesics in space-time don't behave the way they would in the simplest case, and that's gravity. And so general relativity is the geometry of space-time, and gravity is curvature, and that's the punchline, and it's, I don't know, it's been 40 minutes. Thank you.
Thank you, Charlie. I apologize for this time frame. I could have said take 5 minutes here, 5 minutes there.
No.
But what we'll do is, Annie, if you've got this, when you ask questions, you take as much time as you need to answer the question, and maybe anything that was missed in the talk will be picked up in the question. Who's got a question for Charlie? Just to begin. Yes, young lady.
How did you get interested in science?
How did I get interested in science? When I was a little kid, I read kiddie science books, and I grew up in the Washington, D.C. area. I went to museums. It all seemed wonderful and fascinating. Simple as that.
That was almost going to be his talk, and we switched to the theory of relativity. Anyway, who else has a question?
Can we get an email version of the entire presentation?
Sure. Well, I say sure. Oh, okay. All right, my email address is the following. All right, my initials, cf@math.princeton.edu, and I can send you an email version of all the slides. I can't send you the video, but I can send you an email version of all the slides, including the ones that I skipped over. Sure.
One more time for the email address.
Okay. C as in Charlie, F, A, B, C, D, E, F as in Fefferman, at math.princeton.edu.
Yes.
What's the most interesting problem that you'd like to pursue in the future?
Oh, okay. What is the question was, what is the most interesting problem that I would like to pursue in the future? All right, how much optimism would you like to grant me? Oh, okay. I would love to understand turbulence. Okay? I don't pretend that that's going to happen, but I would love to understand turbulence. If you look at some wonderful works of art, there is a drawing of a whirlpool by Leonardo da Vinci with very detailed observation and a lot of, he noticed a lot of stuff that physicists and mathematicians noticed in the 20th century. If you look at the famous painting, The Big Wave by Hokusai, he noticed it too. The artists are ahead of the scientists, and nature is way ahead of everybody, and turbulence is very, very mysterious. And if you see any scientific paper with the word turbulence in it, you should probably take it with a grain of salt, because it's such a difficult problem. And so if you grant me wild optimism, that's what I would like to do.
You'll know when you go on a very smooth flight that Charlie solved the problem.
That's it.
Yes.
When you were pursuing your study of mechanics, what was your greatest motivation?
I simply loved it. So as I studied mathematics, what was my greatest motivator? So the answer is that I loved it. So going back to my interest in science, at some point quite early, I decided, I was no longer satisfied with kiddie explanations. I wanted real explanations. I took a physics book out of the library and couldn't understand a word. So fortunately, my father explained to me that, of course, I couldn't understand it because it has math in it. Well, can I study math? Okay, sure. And so I started studying math, and I fell in love with it. And, well, people are addicted to all sorts of things, and I am addicted to math. And it is just so beautiful that I cannot let go of it. And so I try to work anyway on very, very hard problems that maybe I have a chance of doing, but that aren't a sure thing. And many, many, many times I would love to quit, and I say to myself, okay, this is just too hard, I can't do it. But then the addiction pulls me back, and I go back and think about it.
Yes.
Hi there. So I have a physics question.
Oh, okay, I'm not a physicist, but I will try. Okay.
So, so in regard to the negative component of the time component of the metric there.
Yeah.
So what physical consequences does that have? That's something that I never really understood. There's no negative time.
Oh, okay. So, okay, what it means is that suppose that you light a match, and you look at it goes into a cone, and the equation of a cone has a minus sign in it. So the physical meaning is that it's a cone and it isn't a sphere. I mean, it wouldn't even, how would you even make sense of? Right. I think it's not, I gather from my physicist friends, it's pretty hard to make a physical theory that doesn't predict complete nonsense right away. And if you take general relativity and you refuse to change the plus to the minus, but you think that you're looking at space-time rather than space, I think then you are led immediately to complete nonsense. For instance, how would light spread out when you light a match? One thing I want to mention that I didn't get to, and I'm going to use your question as an excuse. So when Riemann invented Riemannian geometry, he gave a lecture on it in order to get a professorship. In fact, it was a lecture to the assembled faculty of Göttingen in all fields, experts on Persian poetry. And the lecture is preserved. It's beautiful. And he speculates, all right, so geometry need not be like Euclid's geometry. Is that real? Might that actually happen? And Riemann says, maybe because of gravity. geometry is not quite like Euclid's. And well, Riemann didn't have the idea to change the sign, and there were experiments, of course, that led, anyway. But it's remarkable how close Riemann came to general relativity in 1840-something, I think.
I'm a lawyer, so my reasoning process is trying to understand human behavior.
Okay.
How does the mental discipline, the reasoning process that I use in my profession compare to the discipline that you use in terms of geometry and physics, etc.?
I think there are a lot of differences. It seems to me, well, all right, I don't know how much math you know, but I'm sure my ignorance of the law exceeds your ignorance of math, okay? But I have, maybe you're on, all right. I have the impression that, that the law is sort of a codification of what we collectively want. We want fairness, we want, I don't know, freedom of speech, we want contracts not to be broken. There are various things that we want. But the real world is messy, and there are conflicts, and we try to resolve and decide what takes priority over what. In math, it's completely different because, at least I think, well, we've seen examples of excessive confidence, but I think that math properly phrased is just true. And the trouble is that we, our imaginations are maybe too limited to understand it, but it's just true. And so, for example, I think it was Mill who said that in math and in no other subject, all of the argument is on one side of the question. And if you're successful, you prove it, and that's the end, and nobody argues with you. On the other hand, I think the law and math have in common that they are evolving, and humans are taking part in the effort, and we, the understanding gets clearer and changes as time goes on. That's the best I can do, given that I don't know anything about the law.
Yes.
So speaking of imagination, this is a geometric theory. Your examples were all two-dimensional.
Yes.
The third.
Yes.
But of course we know this is three dimensions and times
Yes.
for it.
Yes.
So do you have any tricks or sort of ways to make it intuitive how this, it's higher dimensional behavior? That's the problem, right?
Right.
I'm just wondering, is there...
So is there a trick to visualize four-dimensional things in the mind? I mean, if so, I'd sure like to know one. I think you just, to some extent, you just get used to it. So let's say a one-dimensional world, Lexington Avenue, is a world in which one number is enough to specify what's going on. And a two-dimensional world, let's say Manhattan, is a world in which two dimensions are enough. And if you imagine the Manhattan of the future entirely covered by one enormous skyscraper, then three dimensions, a street, an avenue, and a height would be enough. And so actually, before relativity, there was, let's say, there was statistical physics in which you have spaces of enormous dimensions in which, so for instance, imagine that you have 1 billion particles in a box. And if you have a box full of air, you have a lot more than 1 billion particles. Well, imagine that, all right, each particle is specified by 3 numbers, okay, because it lives in a 3-dimensional world. So to specify all the positions of all billion particles, you need 3 billion numbers. And in order to specify the velocities of those particles, you need another 3 billion numbers. And so altogether, you can think of the complete state of the billion atoms in a box as a single point in a space whose dimension is 6 billion. And it's important to do that. And statistical physics did that before relativity. And in fact, now it's very common to work in infinite dimensional spaces. And if you hear these things for the first time, maybe a natural reaction is fear. But if you're just not afraid, even though you can't see a 6 billion dimensional thing or even a 4-dimensional thing, it's okay.
Was the timing of this talk, did that have anything to do with Einstein's birthday on Monday?
Okay, there we go.
I'm sorry.
No.
Charlie suggested that it was on the centennial of the publication of the theory of general relativity. What?
Show your work. So in fact, exactly what I did not do was to show my work. The original invitation was explain what you, Charlie, have done. And I thought maybe it would be more interesting to explain what Einstein has done, you know, with no false modesty.
Are there any arcane mathematical questions in the 6 billion?
So I don't have an arcane mathematical question, but there are a whole bunch of math students in this room, and I'm just wondering if you have any advice for up-and-coming mathematicians.
Okay.
Or words of wisdom or anything like that.
Let's see. Okay, so I will say a whole bunch of things. Well, I promise this won't take too long, but I'll nevertheless say a whole bunch of things. I think most of them or all of them are obvious, but I think that if there are math students in the room, the harm of not saying something that isn't obvious far exceeds the harm of saying something that is obvious. Okay, so first of all right, if you've decided to study math, it means that you like it. That's great. There are, depending on how far you go, there are lots of fallback positions. So a lovely thing about studying math is that if at some point you decide for any reason that all right, you've enough already, I've suffered enough, you can then there are lots of careers for which the study of math is an excellent preparation. I believe, correct me if I'm wrong, I think you can get into law school having studied math because it proves you can think. Let's see, suppose that you continue. All right, if you go to graduate school in math, it's very, very important to pick the grad school that's right for you. How do you do that? One thing you do is you ask advice of your professors. You also look on the web. You also just apply. It costs nothing. I mean, you apply to a range of places, okay, because it costs basically no time, effort, or money to apply. It's cheap. If money is a problem, you write and say, and almost every place will say, oh, don't worry about it. Talk to grad students who are at one grad school or another and ask them what is their experience. Ask them what it's like to work for a particular advisor, the difference between an advisor with whom you have a good fit and an advisor who's wrong for you is the difference between joy and disaster. So find out by talking, for example, to someone you might like to work with. Hi, I'm a senior, I'm applying to grad school. Are you accepting students? What should I know if I'm your student? Who are your students? Could I talk to them? Let's see. All right, let's see. All right. By that time, okay, at what level are the math students in the room? Should I assume that, let's say, that the words of wisdom should stop once you're in grad school?
I mean, I can't speak for everyone, but many of us, I think, are going on to PhDs at some point.
Sure. Okay. Let's see. I think it's once you're in grad school and you pick a particular area of specialization, there are two things that you should worry about more than anything else, and you'll hear lots of opinions from lots of people. But I think that two things really matter. One is what excites you, never mind what everybody else is saying, and the other is whom will you be working with, and is that person a wonderful, inspiring teacher and a wonderful person or a vicious bastard? Okay, I think that concludes the words of wisdom.
Any last questions? Yes.
It's a very good question. Thank you. If we imagine life,
existence as a space-time continuum,
Yes.
how thick is it? Is it several electrons, and what's behind it?
Okay. So in this, okay, so there are two questions. Let me distinguish very precisely between them. One is, what does general relativity say? And actually three questions. What does general relativity say? What do other more recent physical theories say? And what is reality? Okay. Now, I think I'm best qualified to talk about the first of these questions. What does general relativity say? And in general relativity, simply, all there is this four-dimensional manifold with this notion of the local formula for distances and so on. Okay, so it doesn't, in some sense, space-time doesn't have a thickness. It's think of the surface of the Earth. What is its thickness? It is zero. Okay, and in that same sense, the thickness of the space-time continuum is zero. Now, from shortly after Einstein, physicists have tried to make theories for one reason or another in which there are extra dimensions. But so the world is not just, let's say, 3 dimensions of space and another dimension of time, but there are additional dimensions. How many depends on what year it is. Okay, and why don't we see these other dimensions? Because they're so tightly rolled up. So, for instance, if you imagine a very thin bit of spaghetti, it looks one-dimensional unless you look very carefully, and then it has a certain tiny radius. And so from shortly after Einstein through now, there are physical theories that postulate extra dimensions for one reason or another. And I think just truth in packaging, I'm not a physicist. I'm not qualified to discuss them. Now, what is reality like? I think I know enough to say with confidence, nobody knows. Okay.
May I just, if you have more questions, go ahead. I was going to. Yes.
Do you think that math exists objectively? And if so, does it look anything like our math?
Okay. Wow. Okay. I act as if it has objective reality. It would be very hard for me to function if I didn't passionately believe that with all my being. Is it true? I don't know how one could tell. I don't know how one could tell. It's a reasonable question. Is it about anything? Well, it seems to be about different things depending on when you ask the question. Okay. At this moment in the history of thought, the answer that I think that mathematicians would give you, that I would give you, is that math will tell you logical relationships that are not obvious but that are useful. But it does not tell you absolute truth. It just tells you, if you believe that, then what are the consequences? And well, so, okay.
What I was just going to ask you as a concluding question, which may be foolish, but you hang out with a lot of physicists. It seems that at the upper ends of mathematics and physics, there comes a point when both mathematicians and physicists have to create new language to guide them in their particular discipline. Usually there is an interdigitation between the mathematical languages and the physical languages, as Einstein worked with certain mathematicians when he couldn't do it, or Ulam would tell it. What happens when one goes too far and the other doesn't understand it or is unable to implement it? Does it stymie the research they're doing?
So that's a very, very reasonable question. So I think that the world, all right, wait, how to say this? There are lots of wonderful things to be discovered that we just don't have the imagination to see. And one clue or another makes something just barely possible to imagine. And a very fruitful way to stimulate the imagination is to get input from other fields. And if at some stage in history that the fields become more isolated, progress still happens, but it happens more slowly, and there are lost opportunities. They're not lost forever, but progress can be slow. That's what happens. Let me give you my my little description of what it's like to try to work on a math problem. And I think this resonates with your question. Okay, imagine that you were playing a game of chess against the devil. The devil is much smarter than you. You often do. Okay, okay. Over dinner, over dinner I will tell you a story about a game of chess. But in any event, okay, you play a game of chess against the devil. The devil is much smarter and you are crushed in 15 moves. But you get to take back moves. And so you think to yourself, well, look how the devil crushed me. Well, what happens if I move this piece instead of that piece? Let's see what happens. And the devil still crushes you. And this happens over and over and over again, but you don't give up, and you get to you get to take back moves. And so after a while, you make a clever move, and you are still crushed by the devil, but not in the same way. The devil has to do something else. And so pretty soon you have, well, pretty soon, eventually you have some bag of tricks, and you modify them and you combine them, and with luck, all the time you're getting better. Well, maybe not. You make some terrible mistake and you're crushed in 3 moves. Well, it's not easy to play so badly as to be crushed in 3 moves. But in any event, eventually you win. But while all this is going on, an angel is whispering in your ear, move that pawn, move that pawn. But you are deaf and you can't hear it. But the angel is whispering louder and louder every time, and your hearing is getting better, and you hear hints. That's what it feels like, to, at least for me, to work on math. And so it seems to me that the interaction with other fields causes the angels to whisper a lot more loudly.
Thank you. Thanks for a wonderful talk. Ladies and gentlemen, we do have some questions.